Hello everyone, welcome back. In the last class, we looked at the characteristic of the Euler equations, one Euler equations, and starting from the Euler equations in primitive variable form, we looked at that there are three characteristics: left running, and then entropy, and the right running acoustic. Right. So, if you make the diagram like this, there will be this is u minus a, this is u plus a, and this is u, this is t, and this is x. Right, and corresponding to that, we had basically the compatibility equations. For the left running characteristic, we had this dp minus rho a du. For the right running, we had this dp plus rho a du, and for this u, which is the entropy wave, okay, we just got this entropy equation, right. So, now we will see how we can utilize this information in making our inlet and outlet boundary conditions. So, first thing to note is that our boundary can be inlet and outlet, and how do we distinguish it. So, let us say some flow is coming in and something going out. This is my inlet, this is my outlet. So, how do you mathematically describe it? So, basically we have discussed earlier that there is a normal to the face like this. So, normal is always outward. So, yeah, so like this, and then there will be one on like this, okay. This is n, correct, and let us say my flow is coming from left to right. So, u. So, if you take here vector u, the u dot n, if it is less than 0, so then it is inflow. So, u is on this direction and n is this direction. So, that will be basically negative here. Okay. So, this is basically inflow, okay. And if you take this on the right hand side, normal in this direction, flow is also going out in this direction. This is my n and this is my u. So, u dot n greater than 0, that is outflow. So, flow is going out. Okay, so, this is general definition. If it is a inlet and outlet, let us say internal flow, then it is very easy to say that okay, the flow is coming in from here and flow is going out from here. But let us say you have a domain like this, okay, you want to find out whether it is locally coming in or getting out, then you have to use this u dot n, and which is what we call as u perpendicular. Okay. So, if u perpendicular is less than 0, then it is inlet or inflow. If it is greater than 0, then it is outlet or outflow. Second thing is to note whether it is supersonic or subsonic. Why that is important? Because the characteristic that we saw u minus a, u and u plus a. So, lambda 1 by basically u minus a, this was u and this was u plus a. Okay. So, that depends on whether the flow is supersonic or subsonic. So, if flow is supersonic, that means u is greater than a, right. So, this is positive and this is positive, right. That means the x t diagram that you moved or t x diagrams, all three are basically positive. Okay. So, that means everything is right running, right. So, if you have an inlet like this, so everything will go from left to right like this. Let me see if I have a page here. Okay. Yeah. So, let me make it like this. Okay. So, this is my inlet and this is my outlet. Okay. If it is supersonic, then everything is going on the right. Okay. Then whatever information, whatever, let us say this is my infinity or this is my this is the atmosphere or this is the value outside my domain, outside the boundary. So, everything has to go from this. Okay. So, all the information. So, this is the case of supersonic inlet, right. So, you are not getting anything from interior, you have to specify every single value. Okay. So, if B is my boundary, so whatever u b equal to u infinity, okay, p b equal to p infinity, and rho b equal to rho infinity, and so on and so forth, right. If t b equal v b equal to v infinity, and so on and so forth. On the other hand, if you go for the supersonic outlet, okay, let us talk about the supersonic outlet. What is happening now? Again, it is supersonic and everything is going out now. Okay. So, you see this, these are the three which are all going out, all are positive, u minus a, u minus a, u and u plus a, because u is greater than a, correct. So, in this case it is supersonic outlet. So, you can see that you do not need any boundary condition here, everything is going out from the interior value. So, whatever value that you have, let us say this is my interior boundary here, okay. Let me call it I. So, basically u b equal to u I, okay, p b equal to p I, rho b equal to rho I, okay, and V b equal to V I, and similarly temperature will be. So, everything is coming from this internal point. So, whatever value that you have, you copy it here, whatever value that you have, you copy it here, and so in the case of supersonic, it is the easiest one. At the inlet, you have to specify all the boundary conditions, all the variables would be specified, there is nothing coming out, because that is what you have been saying, that there is no upstream flow allowed in the supersonic thing. So, everything is going downstream, right. Now, this is easy. Now, when it comes to the subsonic inlet and outlet, then it becomes little bit tricky, right. So, let us talk about the now subsonic inlet and outlet. So, when I say subsonic, means u is less than a, that is subsonic. Okay. When you talk about 3D, then u will become basically mod u. Okay. So, this is basically Mach number less than 1, right, u by a is Mach number. So, now it is subsonic. So, now you again have this u minus a, u and u plus a, right. So, u minus a will be negative. So, 1 is coming from this side, and 2 u and u plus a are positive, right. So, this is u plus a, and this is u minus a. So, what is happening? You have to specify one variable from inside, because this u minus a, there is one characteristic which is traveling outward. So, you have to have something going from in to out, okay, one information, okay. Out of 3 variable, at least one variable has to be specified. I mean, in 2D 4 variable, at least one has to be specified like this, okay. And the 2, let us talk about 1D, let us not complicate it for 2D 3D now, we will go to 2D and 3D soon. So, now in 1D you have 3 variables, maybe rho, u and p, right. So, at least one variable has to be specified, because the information has to come from inside to outside. So, typically that variable we choose is pressure. Okay. Remember, we have discussed in the last class that both the pressure and velocity cannot be specified. So, we have pressure coming from basically inside, and the other thing, the rho and u can be specified from because there are 2 characteristics which are traveling rightward. Okay. So, it is coming, you have to give the information, the boundary condition, so that you can come from, you can take the rho and u from there. Okay. Here if you go, this is subsonic inlet. Now, if you go to a subsonic outlet, so subsonic outlet, again you have this 2 going out and 1 getting in, same thing u minus a and u plus a, right. So, 2 getting out means basically 2 you can take from inside, and 1 information has to come from outside. Okay. So, normally what we specify is the back pressure, okay, or it is also called the exit pressure, okay, or boundary pressure, whatever you want to call at the outlet. So, once you have this, so you have 2 information coming directly from the inside. So, whatever the I value that you have, that will be copied, and 1 should come from the right to left, and that will be the back pressure or exit pressure, right. So, once when we will go back to that table. Okay. So, in this case, in the supersonic inlet and outlet, okay, we have either all positive, okay, I mean all the eigenvalues are positive. So, everything is going right running. Okay. So, at the inlet you specify all the boundary condition, at outlet you will specify none. Okay. In the case of subsonic, okay, you have basically 2 going in and 1 going out, right. So, accordingly you have to specify. So, you have given the total pressure and total temperature, I will come to that how it works. Okay. So, I mentioned the rho and u, but from the total pressure you can calculate the velocity u, okay, and the outlet you specify the exit pressure, right. This is again in the text the same thing. Okay. In the case of subsonic inflow and outflow, you have basically only the pressure related information which is traveling, or which has to specify the boundary condition at the outlet. Okay. In the case of supersonic, it is very easy, at the inflow all from outside to interior, and the infinity to I, and here everything from I to infinity, right. No information from outside to interior, no boundary condition is needed at the downstream. So, if you put any boundary condition, it will be ignored if the flow is supersonic. Right. Now, let us come to the multidimensional flow. What happens to the multidimensional flow, right. So, as I mentioned earlier, that you have to always look at the normal value u dot n. So, if it is inflow, then you will see that u dot on n is basically negative, this is inflow, here u dot n is positive, okay, this is outflow, okay, I is interior and infinity is outside. So, this is, you can think of this is my domain, okay. And then you calculate basically the value of u at the boundary, okay, u magnitude. So, that will be square root of u square and v square and w square, okay, and then if it is greater than 1 then it is supersonic, less than 1 that is subsonic, and same thing you can do for outflow also. So, so in the 1D we had basically 3 eigenvalues u minus a, u and u plus a, 3 characteristic basically. So, in the case of multidimensional flow, what will happen that let us say you are talking about the 3D flow. Okay, so then you will have basically u minus a, u and u plus a. Basically, these are the 5 eigenvalues. Okay, so there are 2 acoustic waves still u minus a and u plus a, and I think I should call it u n minus a. Okay, or basically if you want to talk about vector, then it will be basically u plus a n. So, basically what you are talking about is the normal value. Okay. So, you have it you calculate it at the inlet, I mean you calculate this u perpendicular minus a or u perpendicular plus a, these are the 2 eigenvalues, and then also here you have the 3 which is travelling at the speed of u, right. So, the other things remains the same, only thing that you have to take the normal value of that, of the velocity particularly. Okay. In the case of 3 u, one is the entropy wave, okay, as usual for the 1D case. There are 2 more waves, okay, which is still travelling with u. So, basically they represent the transverse velocities. For example, if you have one normal velocity, let us say this is my surface, then there will be one tangential in 2D and there will be 2 tangential u t1 and u t2. Basically, they are 2 tangential velocities. So, basically the gradient of those velocities will be 0. You can just copy the value from the interior, right. So, this is what it represents. So, what is the step? Basically, apply the 1D equation to the normal component. So, basically get the normal component and apply the 1D, and for the tangential velocity component just basically use the simple advection, I mean just like we have been doing earlier. Okay. So, now if you look at the 3D one, so if it is subsonic inflow, then you have 4 entering and 1 leaving. So, why? Because you have subsonic inflow. So, you have lambda minus 1, lambda, lambda, lambda and lambda plus a. So, all 4 are basically right turning positive, one is left turning. So, there will be 1 which is coming out from the interior and there are 4 which is getting in, correct. So, you have to have at least one information coming from inside. So, that is basically you give the pressure which is coming from the CFD solution on the interior point, and at the inlet either you can specify basically rho, u, v and w, and p is coming from interior, okay. Or a better way to do is basically specify total pressure and total temperature and full direction. So, with this and the p from inside you can actually calculate this u, v, w and everything, okay. Basically you have the total pressure, the pressure, and the relation 1 plus gamma minus 1 by 2 m square gamma by gamma minus 1. Okay. So, from basically the temperature you can calculate this Mach number, then calculate the velocity, and from the flow direction you calculate this u, v, w. Okay. So, these are the typical values which are specified, but the important thing to note is that the pressure is taken from the interior, it is extrapolated from the interior. In the case of subsonic outflow, okay, 1 enters and 4 leaves. So, the same case here. So, okay, 1 is coming from inside. So, that we give this basically the static pressure we give, okay, at the boundary, and all other things are extrapolated from the interior. Okay, and the supersonic inflow does not matter, okay, 1 to 2 to 3D, because it is only going in the right hand direction. So, at the inlet you have to specify everything, at the outlet you have to specify nothing. Okay. So, yeah, now let us look at the pressure inlet to make things more clear. How do we calculate this P naught, the velocity from P naught? So, if it is incompressible, then we are specifying, let us say this is my inlet. So, my specifying my P naught here, okay, and we are saying that we have to take one characteristic from inside. So, what we will do, we will take the P which is coming from PCFD, okay, which is coming from the solution at the interior point, first interior point, that value can be used, okay, or the value from the previous iteration. So, whatever value that you have at the previous iteration at this boundary point. Okay. So, from this let us say the P 0 is minus P CFD will be half rho u square or rho v square. Okay. From this you calculate the velocity v, okay, and then basically then you pressure you recalculate the pressure using the CFD equation, you can iterate, and then you can keep on doing like this. Okay. Density does not matter, it is an incompressible flow, okay, you can choose anything. Okay. So, now if it is subsonic flow, then it is slightly different, because now you do not have that relation of the total pressure. You have P 0 equal to P into 1 plus gamma minus 2 m square gamma by gamma minus 1. Now, remember, for the Mach number, the Mach number is u by square root of gamma r t. So, you need the temperature also. So, we also specify the total temperature. Okay. Yeah. So, I think this step should be interchanged. So, you have specified or you have to maybe use some iterative process here. Okay. So, you specify your total pressure and total temperature, okay, and you take the static pressure of the old one. Yeah, I think this is fine. So, you take the static pressure of the old iteration, okay, then you use this P 0 and P to get this Mach number, okay, and from this Mach number you calculate the temperature T, because you have specified T naught also, you get the value of T. From T you calculate the square root of gamma r t, and from that you calculate the value of velocity, which is m into gamma square root of gamma r t, and then you recalculate the pressure using the CFD equations that we have, and then you repeat. Right. So, this is the pressure inlet in the subsonic, and remember one thing here, that when it is subsonic, you know that there are characteristics which are coming out, there are characteristics we are getting in, and the information can flow inside, okay, flow upstream in the subsonic flow. That means, whatever pressure that you are getting, your PCFD that you are taking, or in the previous iteration, they are affected by the boundary condition that you have at the outlet. Right. So, remember we talked about the pressure outlet. So, you have basically some P exit here, right. So, that is affecting here, every time it will be affected. So, your velocity will no longer be constant, okay, because you are calculating velocity using this, okay. The Mach number is changing because your P is changing, although the P naught is fixed, and from that your velocity is not fixed, it is varying in every iteration as the pressure is adjusted. Now, if you go to the supersonic flow, where you have to specify everything at the inlet, okay, all 5 variables, every variable has to be specified. So, what we do, we not only specify P naught and T naught, we also specify P, right. So, then you can write this relation, you can use this relation directly to calculate your Mach number, okay. You calculate the static temperature from this Mach number and total temperature, and finally, you calculate the velocity. So, now velocity is fixed, because your P naught is fixed, your T naught is fixed, okay, and P is fixed. So, the Mach number is also fixed, okay. So, everything is fixed. So, it is basically it is fixed, the velocity is fixed, okay. So, this is the only case that we discussed earlier, that in the case of supersonic flow you can specify both the pressure and the velocity, because every quantity has to be specified, okay. And one thing to note here is that, because there is no reflection from inside to outside, okay. So, that is allowed, that you can specify both the pressure and the velocity, but in the subsonic flow or the incompressible flow you cannot do that, okay. And there is no importance of, I mean, you cannot specify anything at the boundary, because it has to go, all are right lining, so it will go out, right. So, everything will be extrapolated from the interior. There are cases, for example, in the nozzle, for example, if you keep on increasing the back pressure, at some point your SOx will start traveling upstream, right. So, there are special treatments for that. So, basically first you converge and get a solution ignoring the back pressure, and then you iteratively and slowly increase the back pressure till you start seeing some a SOx formation there, and they will travel upstream. So, those are special treatments, and they are actually still challenging problems to simulate when you have a back pressure affecting the supersonic flow. Okay. For example, what happens in scramjet unstart. So, you have the pressure increasing, and because of the increase in the pressure, you have the SOx traveling upstream, and that leads to unstart. Right. So, this is the supersonic flow, everything presented in terms of table. Okay. So, when it is incompressible or it is subsonic, you basically specify the total pressure. Okay. Normally total pressure is better, static pressure also sometimes they specify the total pressure is better, okay. And velocity is adjusted internally, okay. In the case of compressible, you give total pressure and total temperature both, take pressure from inside, okay, and velocity is adjusted. In the case of compressible supersonic, your velocity, because you fix both the total pressure and static pressure and not total temperature, your velocity is specified, it is fixed, it is not changing iteration to iteration. Okay. At the outlet incompressible, you have to give static pressure, you have also give static pressure, okay. And in the case of supersonic, you do not need any boundary condition, okay. So, yeah, so this is how we typically treat the pressure inlet and pressure outlet in most codes, but there are more sophisticated ways to basically treat the inlet and outlet boundary condition, particularly when let us say your domain is not very far, right. So, let us say you are trying to simulate a body like this, but your domain is very I mean not very far from the let us say trailing edge or the leading edge, this distance is not sufficiently far. Okay. Then what may happen is that you may have some reflection coming from here or going from here, which we do not want, okay, if it is not physical. So, you have to use some kind of non-reflective boundary condition, okay, in which what they do is basically they use the characteristic as it is. So, discuss what are the characteristics earlier, okay, derived from the Euler equations. Okay. Remember the W1 and W2 and W3. Okay. So, you have basically del W1 by del W2 plus lambda 1 del W1 by Wx, okay, and so on and so forth. So, you can solve these equations directly, okay, at the inlet and outlet, okay, for different characteristic speeds, and they are called the characteristic non-reflective boundary conditions. Okay. There is another easier way to basically use those boundary conditions, and they are called Riemann, the same Riemann that we discussed earlier, okay, Riemann invariant boundary condition, Riemann invariant based boundary condition. Okay. So, let us look at it. We will not discuss this non-reflective boundary condition. It is a bit involved, but it has the same principle, basically the characteristic equation that we discussed earlier, okay, and you basically have to ensure that there is no reflection. So, whatever thing which are trying to get in the domain, you have to put all those characteristic speeds to 0, okay, or those characteristic variable to 0. We will not be discussing that. There are a paper by Poinsot and Lele, okay, where they have discussed this boundary condition in detail. Okay. So, we will look at a simpler implementation which we call as the Riemann invariant based boundary condition. This is also coming from characteristic, but a simpler implementation. So, what we do is basically from these compatibility equations that we had. So, this if you recall, we had these compatibility equations, okay, dP plus rho A d du equal to 0. Okay. This was for basically u plus minus a, this is plus minus, this is plus minus, okay, and then we also had this entropy equation. Okay. So, in this case a Riemann invariant, what you assume is that the flow is homoentropic. So, what do you mean homoentropic? Basically the entropy is not only constant following a particle, but it is constant everywhere, okay, and here we are talking about the boundaries. So, it is a reasonable assumption to make that flow is homoentropic there. That means there is no mechanism for the entropy to increase there at the boundaries, and that is reasonable because it is sufficiently far from, say, let us say any viscous region or any region where the vorticity can be formed. Okay. So, and then you can assume that homoentropic flow, okay, there is no change in the entropy. Okay. So, ds is equal to 0, okay, everywhere at the boundary, and from that you can try to get invariants called the Riemann invariants. So, basically what are these invariants? These are the invariants which basically as the name suggests, they do not vary across the boundary. Okay. So, we are trying to look at those Riemann invariants. Okay. So, to do that, so now that we are seeing that flow is homoentropic, so we can use this isentropic flow relations. Okay. So, first thing is that the speed of sound, okay, is equal to dP by d rho, and if you use this relation p equal to k root per gamma, you basically get a square equal to gamma p by rho, right, from these two. Okay. So, I will not go into the derivation of this. So, this is known for when you are trying to derive the speed of sound. Okay. Now, we will do some manipulations to get this Riemann invariants. Okay. So, Riemann invariants, as you might have guessed, that it will be in terms of velocity and pressure. If it is the entropy wave, then it will be only pressure, but in the case of other things you will have velocity and pressure, and instead of the velocity, I mean pressure, you will have the speed of sound. We will look at that shortly. Okay. So, we will start with this relation a square equal to gamma p by rho, okay, and then we again replace this p by rho. So, this is p equal to k root to the power gamma. So, basically p by rho will become k root to the power gamma minus 1. Okay. So, the a square has become k gamma k root to the power gamma minus 1, right. Now, again we use the same relation. So, there are some mathematical manipulations here, okay, which we will try to use. So, p equal to k raised to the power gamma and k raised to the power gamma. So, we will replace this row, okay, by this relation a square by gamma k. So, you have basically from this you can write a square equal to gamma k rho to the power gamma minus 1. So, rho will be a square by gamma k 1 by gamma minus 1, okay. And now you have p equal to k raised to the power gamma. So, that means k a square by gamma k to the gamma by gamma minus 1, okay. Now, what we will do, you will take a derivative of this, you will take do dp by dA, take the derivative of p with respect to the square root of sound. So, this k is a constant here, okay, like you know this p v to the power gamma equal to constant, right, for adiabatic flow. So, this same thing will be p equal to k rho to the power gamma, okay, where k is the specific volume, okay, or density. So, dp by dA. So, this will be 1 by gamma k gamma by gamma minus 1, and then you have a square. So, a to the power 2 gamma by gamma minus 1 d by dA, right. And if you look at this term, okay, so this is how, so n a n minus 1, right. So, what is this, dx n by dx is equal to n x n minus 1, right. So, the same thing will apply here. So, this will be 2 gamma by gamma minus 1 will come out, okay, and then this will be a to the power 2 gamma by gamma minus 1 minus 1, right. So, this will become a to the power gamma plus 1 by gamma minus 1, right. So, then this is a to the power gamma plus 1 by gamma minus 1. So, this is the value of dp in terms of dA, right. So, all this part remains preserved here, and this 2 gamma by gamma minus 1, and this become a to the power gamma plus 1 by gamma minus 1 into dA. Why I am doing this, it will become clear shortly, okay. So, now I am trying to rearrange it. So, this is the relation that we have, okay. So, I have taken 2 by gamma minus 1 into dA, and then this I have separated all these terms. Now, if you look it closely, this is nothing but rho a, okay, because rho was this, okay, and you multiply with a here. So, this is a to the power 2 by gamma minus 1. So, then it becomes a to the power gamma plus 1 by gamma minus 1, you multiply with a here, right. This is a to the power 2 by gamma minus 1 plus 1, right. So, this will become a to the power gamma plus 1 by gamma minus 1, right, and the bottom one is the same, right. So, we can replace this entire thing by rho a, right. So, this will become dp is equal to rho a 2 by gamma minus 1 into dA, right, and then finally, you can write it as dp by rho a is equal to 2 by gamma minus 1 into dA, right. Now, we will integrate it, okay, and we will integrate it along different characteristic that we have. So, let us say if you are doing C plus characteristic, which is basically u plus a, right. So, you know this characteristic dp plus rho a du equal to 0, right. So, basically dp by rho a is equal to minus du, right. So, you use this value here and this is equal to 0. So, basically you will have get the characteristic which is by integrating this u plus u by 2 a by gamma minus 1 is equal to constant, along of course, dx by dt equal to u plus a, which is C plus. So, this we call as the J plus characteristic, basically the right running characteristic or the positive sorry not characteristic, the Riemann invariant. So, this is J plus. Similarly, if you do along C minus, so that will be dp minus rho a du equal to 0, and that will give you another relation which is u minus 2 a by gamma minus 1 equal to constant, okay, which is called J minus. And finally, you all have already have h equal to constant along dx by dt equal to u. So, we got two invariants, Riemann invariants, one is J plus and another is J minus, and the relation is they are constant, okay, along these lines. So, whenever you have this dx by dt equal to u a, so let us say you are talking about this inlet here, okay, there is u minus a, there is u plus a and there is u, right. So, I am saying that around u minus a the value is constant, okay. So, whatever the value at the boundary, so let us say my j minus at boundary will be equal to j minus at interior point, because that is the Riemann invariant, that is the definition that along this dx by dt equal to u minus a, this variable is constant. Similarly, if you look at u plus a, that will be j plus b will be coming from this side. So, that will be j plus infinity, let us say my infinity condition here, right. So, once you know this, you can from the interior you can calculate this j minus, from the exterior you can calculate this j plus, okay. And once you have calculated it, so now let me call it. So, this will be from j plus b will be basically u b plus 2 a by gamma minus 1, and j minus b is equal to u b minus 2 a by gamma minus 1, which can be calculated using, for in this particular case, that will be g plus infinity and j minus I, right. So, from you know this value from the infinity, you know this value from the interior. So, once you know this and this, okay. So, if you want to get this u b, so you just can just add that and then take the division. So, the u b is equal to j plus b plus j minus b by 2, and similarly you can manipulate and you can get the value of a also from this, right. So, yeah, one more point that I want to make it here, like I mentioned earlier also, that you cannot specify u and p at the inlet, okay. If you specify both this velocity and the pressure variable, then what will happen that you have some invariant coming from inside and some going from outside, okay. If you can satisfy the maybe the right going one, the u plus a or the j plus, it will not satisfy the u minus a, okay, or the j minus. Okay. So, that is another reason why we cannot basically use both the pressure and the velocity in the case of subsonic or the compressor flows. It is violating the essential physics that we have. Okay. So, how do you do this for the subsonic flow? Okay. So, let us say the Mach number is less than 1. Okay. So, one is coming out of the domain. So, one is like this u minus a and another is u plus a. Okay. So, from the boundary conditions you calculate the j plus, okay, this is u plus a. So, from the boundary condition, whatever infinity condition you have, you can give p 0 t 0 or maybe rho u and other things, okay. And you calculate this u plus a. From the interior cell you get this u minus a, I mean which is j minus, and now you take add both of them and divide by 2, that is u b, and then you subtract and into multiply by gamma minus 1 by 4, that will give you the speed of sound at the boundary. So, you have gotten the boundary speed and the a b. You can put in the ghost shell also if you want, okay. In the finite difference you can just use at the boundary point, in the finite volume you can use as the ghost shell, so that the boundary values becomes like this. So, once you have gotten the u b and a b, you can calculate basically the other things. For example, you can calculate the T b based on a b square by gamma r, okay. Then you can have rho b, okay, which is P b by r T b, and then you can also use this relation P b to get the from the P 0 and I mean from the isentropic relation you can do that, okay. And finally, if you have subsonic outflow, you have similar thing. So, basically you are fixing this P b equal to P exit, okay. So, the P b is already known, okay. So, j in basically j plus, so it will come from this, okay. You can calculate using the interior cell whatever value that you have at the interior point, and from this you can calculate the solve for u b and a b. So, P exit is known, rho b you have to assume either you have to iterate or you have to assume that P b rho b is as the rho interior, okay. And then you can calculate u b using the j minus relation, sorry j plus relation, and then you can also get the T b. So, you have gotten all the variables, okay. And so, yeah, if it is far field you can use the same Riemann invariant at the far field also. The crux is to find out whether it is locally inflow or outflow, locally supersonic or subsonic, okay. If it is so, for that you have to get this u dot n, okay, that u normal, okay, that will give you, if it is greater than 0 then it is outflow, if it is less than 0 that is inflow. Next you calculate this u magnitude, okay, and say if it is less than a or greater than a. If it is less than a, then it is subsonic, if it is greater than a, then it is supersonic. So, you determine whether it is supersonic inflow, supersonic outflow, subsonic inflow, subsonic outflow, and accordingly you can, if it is supersonic inflow outflow, you just have one direction of the flow, you can directly use those values. If it is subsonic inflow or outflow, you have to basically calculate those value using subsonic relation. So, yeah, I think yeah, if it is the multi-dimensional flow, just last point I want to say, as I mentioned earlier, that there is a tangential velocity, okay. So, there is a normal velocity which will be used for the entire calculation, but for the tangential velocity we say that we will just take it from the interior point, okay. It is not changing, the gradient basically LUT norm in the normal direction is equal to 0. Okay, the tangential velocity is not changing in the direction. So, you can just take those values and then you have to reconstruct it. Okay. So, you get this u at the boundary, but the normal one. So, you have to specify u equal to u n n x plus u t t x. You can do it for the interior point and the on the external point, and then finally, you calculate this u and b using the Riemann invariants by only considering the normal component either interior or infinity. Okay. And then finally, once you constructed it, the tangential velocity remains the same, you reconstruct it back for u b and v b. Similarly, you can do for the 3D also. In that case, you will have one normal and there will be two tangential u t 1 and u t 2. Okay. So, basically you have to, these things will not change, you can extrapolate from interior, u n will be dictated based on the Riemann invariant, and you have to basically use relations like this to finally construct it in the global coordinate system that you are using. Okay. So, yeah, this is what I have for the boundary conditions. So, we discussed about the wall, the slip and no slip, the symmetric boundary condition, then the periodic boundary condition, okay, axisymmetric boundary condition, and finally, we discussed a variety of boundary conditions like inflow and outflow, okay, for incompressible, compressible and supersonic, Mach greater than 1 or less than 1 both. Right. So, there are more there are other for any flow that you want to study, the boundary conditions are very important, okay, and you have other boundary conditions like the interface boundary conditions, flow is just going, then you can have the fan boundary condition, or if you are using a propeller, then you have to model the propeller. So, accordingly you have to provide the boundary condition. Okay. So, there are several boundary conditions. If you look at open form, there is a list of boundary conditions, more than maybe 50 boundary conditions. Okay. There is a fixed velocity, then you have inlet, outlet, there is a boundary conditions like Robin boundary conditions. At some point it can go to Neumann, other point it can go to the Dirichlet. Okay. So, it can go to the fixed value or it can go to the gradient 0. So, all those kind of things are there. So, more you study or if you start coding, you can take the basic Q from here and write your own boundary conditions in your code. Okay. So, with that we will stop here, we will meet you in the next class. Thank you very much.